Running a modern trillion-parameter AI model requires an astonishing amount of computational power. Trillions of calculations happen every second as data flows through the network. But this computational intensity creates a critical physical vulnerability. To actually perform these mathematical operations, a process called forward propagation, the model's internal weights and the user's prompt must be fully decrypted and stored in the server's random access memory. This creates a complex dynamic between three distinct parties. We have the model owner, the data owner, and the service provider. The model owner spent millions training their AI. They need to protect their proprietary architecture and weights from theft. The data owner submits highly sensitive inputs, like proprietary corporate data. They need absolute assurance their data cannot be logged. The service provider simply rents out server racks, wanting to host this infrastructure without the liability of accessing either party's data. Because all this data sits completely exposed in the provider's memory during processing, standard cloud deployments suffer from an inherent trust gap. Everyone is forced to simply trust the host. The traditional way we secure data in the cloud is through software isolation. We build virtual private clouds, use isolated containers, and run separate virtual machines. But software isolation relies on the underlying system acting in good faith. If the operating system kernel or the hypervisor is compromised, or if a cloud operator acts maliciously, those software rules can be bypassed to scrape the raw, plain-text data directly from the host's memory. While standard software isolation is the baseline for most cloud services, it falls short of the requirements for zero-trust AI. Protecting these assets requires moving to silicon-level trusted execution environments and advanced cryptography. We need to remove human trust from the equation entirely. The cloud provider itself must be physically and mathematically locked out of the processing layer. To build this system, we start by stripping away the software layers and looking directly at the silicon of the cloud host server. Modern server processors feature technologies like AWS Nitro, Intel TDX, or AMD SEV SNP. These allow us to carve out a trusted execution environment, a secure enclave right at the hardware level. The primary guarantee here is physical isolation. The CPU itself blocks the host operating system and hypervisor from reading any memory assigned to this enclave. Furthermore, all debugging, tracing, and monitoring features are permanently disabled inside this boundary by the hardware itself. The only way in or out is through a strictly defined communication tunnel. But if the host is inherently untrusted, how do the external parties actually verify this? How do they mathematically prove they are sending data to a genuine secure enclave and not just a spoofed virtual machine? The solution is the hardware root of trust, typically a Trusted Platform Module, or TPM, located right on the server's motherboard. When the server boots up, it performs a measured boot. The TPM hashes the exact state of the operating system and the workload binaries, storing these cryptographic measurements into specific hardware registers. The hardware then generates an attestation document. This is a cryptographic proof, signed by a trusted root key embedded in the silicon, verifying the exact untampered state of the code running inside the enclave. The hardware isolation creates the physical lockbox, while the cryptographic attestation provides the mathematical proof of exactly what code is inside it. With the enclave verified, the external parties can securely interact with the service. The data owner establishes an end-to-end encrypted TLS tunnel that terminates directly inside the hardware enclave. The service provider still physically routes these encrypted packets over their network, but they lack the keys to decrypt them. They can never read the plain text prompt. The model owner uses a similar verification process to deploy their proprietary weights. The enclave sends its cryptographically signed attestation document out to the model owner's external key management system. The key management system verifies the hardware hashes against the expected pre-approved code. If a single byte doesn't perfectly match, the system denies access. Once verified, the keys are delivered. This allows the enclave to pull the encrypted model weights from standard cloud storage and decrypt them entirely internally. As a result, the user's private inputs and the proprietary model weights only ever meet in plain text inside this mathematically verified hardware-locked space. This setup works flawlessly on a CPU, but a CPU alone isn't powerful enough for trillion-parameter inference. We have to use AI accelerators, like GPUs or NPUs. Moving decrypted data from the secure CPU enclave over to the GPU creates a massive vulnerability. As data travels across the PCIe bus on the motherboard, it is entirely exposed to interception. To secure this bridge, we implement strict CPU core allocation. This limits hardware-level PCIe access solely to the specific CPU cores designated to the trusted execution environment. Next, the system uses hardware-enforced write-only memory. Input parameters are loaded from the CPU directly into a locked memory range on the accelerator that only the accelerator can read. The accelerator processes the inputs and writes the outputs directly back to a separate locked memory range inside the CPU enclave, bypassing the host operating system completely. This complex choreography extends the secure confidential boundary seamlessly across the physical gap between processors. The hardware successfully secures the execution at runtime. But there is one final systemic risk. What if the enclave binary itself is malicious? If the build environment is compromised in a supply chain attack, a threat actor could inject a backdoor specifically designed to leak those decrypted weights directly out of the enclave. We need absolute binary assurance before the code is ever hashed into the hardware registers. This requires a highly hardened build environment, paired with shared or open-source codebase auditing. The parties involved must be able to inspect the code line by line. Achieving zero trust means all three parties must independently audit the software before the hardware permanently locks it down into production. Let's reevaluate this entire architecture by placing it under the stress of a worst-case scenario. Assume a highly capable threat actor has gained total root and administrative control over the physical host machine and the surrounding network. Network sniffing yields nothing. The storage buckets only hold encrypted weights, and the data owner's tunnel is completely protected by end-to-end encrypted TLS. Even with root access, hypervisor tampering fails. The hardware root of trust and memory encryption physically block the attacker from scraping the RAM. And if they try to spoof the virtual machine entirely, the model's key management system will instantly reject the attestation document because the hardware hash won't perfectly match the audited binary. This means that even with administrative control over the machine, the attacker is physically excluded from the encrypted memory and the isolated processing cores that hold the sensitive parameters. This architecture translates directly to real-world AI deployment requirements and security policy. Research institutions like RAND define security levels 4 and 5 specifically for systems built to withstand leading cyber-capable institutions and nation-state actors. As frontier models begin to demonstrate highly dangerous capabilities, these extreme security measures become mandatory to prevent global proliferation and theft. Confidential computing removes the human element entirely. We no longer have to trust the operators hosting the physical machine. For the future of frontier AI, confidential inference provides the specific architectural safeguards that make global deployment a viable reality.